What is the specific problem that InternLM-XComposer-2.5, IXC 2.5, aims to solve in the field of large vision language models, LVLMs?
InternLM-XComposer-2.5, IXC 2.5, aims to solve the specific problem of bridging the gap between proprietary APIs and open-source large vision language models, LVLMs, by providing a versatile LVLM that supports long-contextual input and output with diverse comprehension and composition capacities. The model addresses the limitations of existing open-source LVLMs, which struggle with performing diverse vision language comprehension and composition tasks due to restricted training corpus diversity and challenges in managing long-context input and output. IXC 2.5 excels in versatility by supporting a wide range of tasks such as free-form text-image conversation, OCR, video understanding, article composition with illustrations, and web page crafting. Additionally, it enhances long-context capabilities in both input and output, empowering human-AI interaction and content creation. By incorporating extra LoRa parameters for text-image composition, IXC 2.5 also addresses the issue of open-source models lagging behind closed-source leading paradigms in versatility.
How does the proposed method of IXC 2.5 work? Illustrate step by step.
The proposed method of IXC 2.5 works through a comprehensive approach that involves several key steps. Firstly, during the pre-training phase, the large language model, LLM InternLM-2.5 is frozen, while the vision encoder and partial LoRa are fine-tuned to align the visual tokens with the LLM. The model architecture mainly follows the design of InternLM-XComposer-2 and InternLM-XComposer-2.5 KHD, including a vision encoder OpenAI VIT-L14, large language model InternLM-2.5, and partial LoRa for efficient alignment. The model supports diverse input modalities, including text, single multiple images, and videos, utilizing a unified dynamic image partition strategy for videos and multiple images with any resolutions and aspect ratios. For image processing, a dynamic image partition and global local format design is employed, with a VIT resolution increased to 560 by 560 and a scaled identity strategy for high-resolution images. In video processing, frames are sampled and concatenated to form a high-resolution image, with the frame index included for temporal relation. Audio input and output are supported using open-source tools like Whisper for transcription and MeloTTS for audio conversion. During supervised fine-tuning, the model is fine-tuned with a focus on handling extremely large images and videos, with a maximum number of partitions set to 24 for the unified dynamic image partition strategy. The model is trained with large images concatenated by up to 64 frames, with a training context window size of 24,000. The model is jointly trained with a batch size of 2048 over 4,000 steps, with data sampled in a weighted manner based on the number of data from each source. The model is fine-tuned using a fixed learning rate scale factor to balance preserving its original capabilities and aligning it with vision knowledge. In the context of web page generation, the model is enhanced to autonomously construct web pages based on visual screenshots, free-form instructions, or resume documents. The model is trained using datasets from website v0, 1v0, 2 and Stack v2 for tasks like screenshot to code, instruction-aware web page generation, and resume to homepage generation. The model is proficient in generating JavaScript code, enabling the development of interactive front-end web pages. The model's capabilities are further extended to include generating high-quality text-image articles through a scalable pipeline that integrates supervised fine-tuning, reward modeling, preference data collection, and direct preference optimization (DPO) alignment for stable and high-quality article generation. Through these steps, IXC 2.5 demonstrates competitive performance across various benchmarks, showcasing its versatility and effectiveness in handling diverse tasks in the realm of large vision language models.
What are the theoretical or practical benefits of using IXC 2.5 compared to existing LVLMs?
The theoretical and practical benefits of using IXC 2.5 compared to existing LVLMs are significant. The model excels in versatility, supporting a wide range of tasks related to comprehension and composition, such as free-form text-image conversation, OCR, video understanding, article composition with illustrations, and web page crafting. IXC 2.5 also stands out in its long-context capabilities in both input and output, being natively trained with 24K interleaved image text data, which can be extended to 96K through positional encoding extrapolation. This empowers long-term human-AI interaction and content creation. Additionally, IXC 2.5 enhances comprehension abilities, such as ultra-high-resolution understanding, fine-grained video understanding, and multi-turn, multi-image dialogue. It also supports crafting web pages and composing high-quality text-image articles, leveraging techniques like chain of thought (COT) and direct preference optimization (DPO) to enhance content quality. Furthermore, IXC 2.5 achieves state-of-the-art results in various benchmarks, surpassing both open-source LVLMs and closed-source APIs in multiple tasks, showcasing its superior performance and competitiveness in the field.
How was the method of IXC 2.5 validated or tested according to the paper?
The method of IXC 2.5 is validated or tested through a series of experiments on various benchmarks to assess its performance. The paper reports the benchmark results of IXC 2.5 on tasks such as video understanding, structural high-resolution analysis, general visual question answering, multi-image multi-turn dialogue, and web page crafting. The validation is conducted using the OpenCompass VLM Eval Kit for unified result reproduction. For instance, in video understanding benchmarks, IXC 2.5 outperforms open-source models on 4 out of 5 benchmarks and matches closed-source APIs. In structural high-resolution benchmarks, IXC 2.5 performs on par with large open-source LVLMs and closed-source APIs. Additionally, in multi-image multi-turn benchmarks, IXC 2.5 shows superior performance compared to previous SOTA open-source models. Furthermore, in general visual question answering benchmarks, IXC 2.5 demonstrates excellent performance, surpassing GPT-4v and Gemini Pro in some cases. Lastly, in the screenshot-to-code benchmark, IXC 2.5 even surpasses GPT-4v on average performance, showcasing its potential in bridging the visual design and code implementation gap. These comprehensive benchmark evaluations validate the effectiveness and competitiveness of IXC 2.5 across a range of tasks and domains.
What results were achieved with IXC 2.5 in terms of benchmark performance, and how does it compare to other models like GPT-4v and Gemini Pro?
IXC 2.5 achieved state-of-the-art results in 16 out of 28 benchmarks, matching or surpassing proprietary APIs like GPT-4v and Gemini Pro in 16 benchmarks. For example, in video understanding benchmarks, IXC 2.5 outperformed open-source models on 4 out of 5 benchmarks and performed similarly to closed-source APIs. Specifically, on the MV-Bench benchmark, IXC 2.5 achieved a score of 69.1, which was 7% higher than the previous SOTA method video chat, 2 to 7b, and 6% higher than GPT-4v. In structural high-resolution benchmarks, IXC 2.5 performed on par with large open-source LVLMs and closed-source APIs, such as reaching 99% on the DOCVQA test set, matching INTERNVL-1.5 with significantly fewer parameters. In multi-image multi-turn benchmarks, IXC 2.5 excelled by outperforming the previous SOTA open-source model by a substantial margin of 13.8%. Additionally, in general visual question answering benchmarks, IXC 5 demonstrated superb performance, achieving 59.9% on MM* and surpassing GPT-4v and Gemini Pro. Lastly, in the screenshot to code benchmark, IXC2.5 even surpassed GPT-4v on average performance, showcasing its potential in bridging the visual design and code implementation gap.
What are the limitations or drawbacks of using the method of IXC2.5?
The limitations or drawbacks of using the method of IXC2.5 include the reliance on supervised fine-tuning with a limited amount of instruction data, which can lead to unstable responses from LVLMs in certain cases. Additionally, the process of generating high-quality text-image articles is challenging due to the scarcity and expense of collecting such articles, which may hinder the model's ability to consistently produce satisfactory results. Another drawback is the need for a reward modeling process to label responses, which adds complexity to the training pipeline and requires additional resources for data labeling. Furthermore, the preference alignment technique used in IXC2.5 focuses on minimizing the likelihood of dispreferred responses rather than maximizing the likelihood of preferred responses, which may impact the model's ability to generate diverse and creative content. Lastly, the method of aligning the model with vision knowledge through partial LoRa fine-tuning may introduce biases or limitations in the model's understanding of visual content, potentially affecting its performance on certain tasks.